Alright, so in this video we're going to be going over some properties of solutions, how to separate them, and just some different vocab terms. So when we're looking at solutions, they are homogeneous mixtures. Now homogeneous mixtures can be all states of matter. It can be gaseous, it can be solid, so steel would be a homogeneous mixture, not necessarily a solution though. A solution consists of two things. It has a solute and a solvent. And usually the solvent will be found in greater amounts, or will always be found in greater amounts. So you're going to dissolve the solute into the solvent, and these solutions will not scatter light, and they can't be separated by filtration. So you can't separate salt from water by filtering it. Now a colloid has larger particles. They can appear to be homogeneous, but if you look under a microscope, they actually are heterogeneous. They do not look uniform, and they can scatter light. So basically, if I try to shine a light through a colloid, the light will either be reflected away, or you can actually see the beam forming in that colloid. That will not happen with a solution. Basically, if I put a light through it, it just goes straight through. So if I were to separate a solution, we're going to use usually two different ways to do that. We can use distillation, or we can use chromatography. So with distillation, basically we're going to be using boiling points to separate the components of a solution. So if you have different boiling points, you can separate it with this apparatus right here. Okay, so basically what you have inside this flask is a mixture of water and ethanol. Well, water will boil at a different boiling point than ethanol will. Ethanol usually starts to boil first. It'll boil at a lower temperature. So basically you'll slowly heat this mixture up. The thing with the lower boiling point will start to evaporate, come up, and then go through this condensing tube, and then will liquefy through this beaker. So after you start boiling it, ethanol will be first because it has a lower boiling point, goes through the condensing tube, and then inside this beaker you'll have just ethanol. So you should see just your ethanol molecules right here. Now, what you'll do at this point, once you get all of your ethanol, so at 78 degrees Celsius, that's when ethanol starts to boil, you'll have collected all of your ethanol. You can pour it out and then basically boil out the water. So your water will start to boil at 100 degrees Celsius. And then once that happens, it goes through the condensing coil, and then out it comes through the beaker. So then at that point, you should have your water molecules. So basically distillation works by separating out components of the mixture through their intermolecular forces. Because remember, if you have a higher intermolecular force, you're going to have a higher boiling point. Alright, so chromatography can also be used to separate solutions out. Basically, you're going to put a sample on something called a stationary phase. Usually it's some piece of paper. Okay, so you'll have your sample. You'll put a small amount of that sample, and basically you will put it in a solvent. That solvent is called a mobile phase because it will run up the paper or up the stationary phase. So this is paper chromatography. There's all sorts of chromatography out there, but this is the one that you'll probably see on the test. Basically what will happen is as the solvent runs up, components in that mixture will bind to the solvent if they're attracted to it. So if their intermolecular forces are attracted to the mobile phase, they'll move further up the paper because they're attracted to that solvent. Well, the distance that they travel up the paper is going to be measured, and we're going to get something called a retention factor. The retention factor is the distance traveled by the thing in your mixture divided by the distance traveled by the solvent. So once you have that, you can compare RF values to a known component to decide what it is, and also you can compare the intermolecular forces of the components inside that mixture. So this is what it looks like. So basically what you'll do is you'll take your mixture, you'll put it onto a stationary phase or a piece of paper, and then you'll let the solvent run up it. Well, different components of your mixture will start to separate, and they separate because some of the components will be more attracted to the solvent or the mobile phase than other components. So if I were to take a nonpolar solvent right here and put it onto the paper, so let's say that I have a nonpolar solvent. If it's a nonpolar component, it's going to be further up the paper. Polar components will be lower down on the paper because they're not as attracted to that nonpolar solvent. So the more attracted it is to the solvent, the further up the paper it goes. So if it's polar and there is a polar solvent, it'll be further up the paper. If it's a nonpolar solvent, though, it'll be lower on the paper. All right, so when we make a solution, it goes through various stages. So the first stage is basically to separate out the solute particles. So if we have like a sodium chloride, well, they're attracted to each other because of the positive and the negative charge. So in order to make the solution, we're going to have to separate them out. Well, in order to do that, we have to put energy into that process because we're trying to pull two things that are attracted to each other apart. So that's going to require energy. Now, the second part is to separate the solvent particles. So if I have water molecules, like this, they are also attracted to each other by hydrogen bonding. So we have to break those hydrogen bondings or bonds. So then that is also going to require energy. The next step is to solvate. So basically when the solute and the solvent interact, that is going to release energy because now I'm putting things together that are attracted to each other. So if I'm pulling things apart that are attracted to each other, that's going to require energy. But if I put things together that are attracted to each other, that should release energy. So whether this whole process is endothermic or exothermic depends on how the magnitude of this step. So this requires energy, this requires energy, this releases energy. So if this releases more energy than the energy we had to put into it, it ends up being exothermic. Okay, so if we dissolve something, this is what it should look like if we dissolve something in water, ionic. So you might be asked to draw a particle diagram. You'll definitely be asked to interpret them. So if we look at this molecule, or this particle diagram right here, sodium is positive, so therefore when it's interacting with the water molecules, it should be interacting with the negative end. Chlorine should also be interacting with the water molecules, but on the positive end. So the negative end will be the more electronegative atom, and that should be interacting with positive charges. And then chlorine, which is negative, should be interacting with the positive charges of the water molecules. And when you draw these particles, you need to make sure you pay attention to size because they will be looking at that. Sodium, since it's positive, has lost electrons. Oops. So that means it should be smaller than the negative ions. And then these are just good rules of thumb to remember. So if you're going to draw particle diagrams with water, draw at least 3 water molecules around each thing so they can actually see what you're trying to get them to visualize.